Welcome to The Explainer. Today, we're going to decode one of nature's most powerful and, let's be honest, most misunderstood phenomena, nuclear radiation. We're going to break down what it is, where it comes from, and how it shapes our world in ways you might never, ever expect. So let's start with a wild question. What if the very atoms that make up, well, everything, were constantly falling apart? It sounds a little scary, right? Like something out of a sci-fi movie. But in a very real way, that's exactly what's happening all around us. Our world is filled with atoms that are fundamentally unstable, and that instability is the source of all nuclear radiation. To really wrap our heads around radiation, we have to think small. Like, really small. We've got to zoom all the way down to the level of a single unstable atom. This is where the whole story really begins. It all starts right here, inside the nucleus of an atom. You can think of a radioactive nucleus as being, well, super jittery. It has way too much energy, and its one and only goal in life is to calm down, to reach a state of stability. And the only way it can do that is by getting rid of that extra energy. Now, this instability isn't just random. It's actually a constant battle between some of the most fundamental forces in the universe. Inside that tiny nucleus, you have all these positively charged protons, and they are desperately trying to push each other apart. When that repulsive force starts to overpower the forces holding everything together, well, the atom has to shed some parts of itself to find balance. And that process of shedding, that is radiation. So, when a nucleus releases all this pent-up energy, it does so in a few very distinct ways. And a great way to think about them is as the radiation alphabet. Each one has its own unique personality and power. First up, we've got the heavyweight of the group, the alpha particle. This is the biggest and the bulkiest form of radiation. Just think about how substantial this thing is. An alpha particle is literally a helium nucleus. That's 2 protons and 2 neutrons blasted out of the original atom. And because it's so big and heavy, it's kind of slow. It can't travel very far, and it has almost zero penetrating power. A simple piece of paper is enough to stop it dead in its tracks. Okay. Next up in our alphabet is the much lighter, much faster beta particle. And this one is a completely different beast. A beta particle is basically a supercharged electron. But what's so fascinating is where it comes from. It's actually born right inside the nucleus when a neutron suddenly transforms into a proton. And because it's so much smaller and lighter than an alpha particle, it has way more penetrating power. It'll zip right through paper, but it can be stopped by something thicker, like a heavy lab coat. And finally, we get to gamma rays. Now, these aren't particles at all. And this is where radiation gets seriously powerful. And here's the key difference. Gamma radiation is pure energy. Think of it like an ultra-powerful X-ray. It has no mass, no charge, it's just a wave of energy. And because of that, it can pass through most materials like they're not even there. To stop gamma rays, you need some seriously dense shielding, like thick sheets of lead or several feet of concrete. So this table just gives us a fantastic side-by-side look, and the difference is staggering, right? An alpha particle fizzles out after just a few centimeters in the air. It can't even get through the top layer of your skin. But, and this is a huge but, if you were to ingest something that emits alpha particles, they suddenly become incredibly dangerous because they release all that energy directly inside your cells. A gamma ray, on the other hand, can travel 500 meters and can pass straight through your body. This is why different types of radiation pose such different kinds of risks. Okay, so if radiation is this invisible force, how in the world do we detect it? You can't see it, you can't smell it, but it turns out we have some really clever ways of making it visible. You know that classic clicking sound you always hear in movies? That comes from a Geiger counter. It's basically a metal tube filled with a gas, usually argon. When a particle or ray of radiation zips through that tube, it knocks electrons off the argon atoms. That creates a tiny little electrical pulse, and the counter amplifies that pulse into an audible click. So every single click you hear is one single radioactive event being detected. But just detecting it isn't enough. To understand the impact radiation has on us, we need a special unit called the REM. And this is so important because a REM doesn't just measure the raw amount of radiation, it measures the potential biological damage it can do. It's a way of leveling the playing field because it accounts for the fact that a dose of alpha radiation has a totally different effect on your body than the exact same dose of gamma radiation. And to put all that into perspective, check this out.
We measure these doses in millirem, which is just 1,000th of a rem. A single dental X-ray is about 20 millirem. The annual limit for someone who works in a nuclear facility is 2,000. But a dose that's lethal to about half the people who get it, a mind-boggling 500,000 millirem. The scale is just absolutely enormous.
But here's where the story takes a fascinating turn. Radiation isn't just a hazard. It's also one of our most powerful tools. It is truly a double-edged sword. And this really gets to the core of it. The very same property that makes radiation dangerous is also what makes it a life-saving medical tool. See, radiation is most harmful to cells that divide really, really quickly. That's why it's so damaging to things like our bone marrow. But you know what else divides rapidly? Cancer cells. So doctors can use these incredibly focused beams of radiation to target and destroy tumors while doing as little damage as possible to the healthier, slower dividing tissue around them. And it's not just for medicine. In one of its most amazing applications, radiation can act as a kind of atomic clock, letting us date ancient artifacts with incredible precision. The way this works is just brilliant. As long as any organism is alive, a plant, an animal, us, it's constantly taking in a tiny, steady amount of radioactive carbon-14 from the environment. The second it dies, that intake stops cold. And from that moment on, the carbon-14 it already has inside starts to decay at a perfectly predictable rate. So, by measuring how much is left, scientists can calculate almost exactly how long ago it died.
And this whole amazing process is possible because we know this one magic number, the half-life of carbon-14. Every 5,730 years, exactly half of the carbon-14 in a sample will have decayed away. It is one of nature's most reliable and incredible clocks.
All right, now for the final and maybe most surprising piece of the puzzle. Radiation isn't some far-off concept you only find in labs or power plants. It is all around us, every single day. You might be pretty surprised to learn that the single biggest source of natural radiation for most of us is something called radon gas. It just seeps out of the ground from the natural decay of uranium in rocks and soil. On top of that, we're constantly being bombarded by cosmic rays from space, and we even ingest tiny amounts of radioactive material in the food we eat and the water we drink. It's just a natural part of living on planet Earth. So, when you get right down to it, radiation is this natural, powerful, fundamental part of our universe. It's not inherently good or evil, it's just a force of nature. Understanding it is the key to minimizing its risks while harnessing its incredible benefits, from healing the sick to unlocking the secrets of our ancient past. The real challenge, then, is ours, to learn how to wield this unseen force wisely.